Hi there, my name is Bernardo Malaca, a master's student at IST, and I'm working at the Group for Lasers and Plasmas. I'm here to tell you about my master's thesis, Machine Learning Controlled Plasma-Based Acceleration. Confused? Keep up with me. Let's start with the plasma acceleration part. Our plasma accelerator, as the name already tells, is composed of plasma. Plasma is the fourth state of matter, a gas that is ionized and is highly electrically conductive, and where collective phenomena of electrons and ions dominate the dynamics. One of the most promising accelerating mechanisms is the LWFA, which goes by laser wake field acceleration. When a boat enters the water is perturbed, with a wave forming behind the boat. This is exactly what happens when the laser enters a plasma. The laser creates a plasma wave behind it. This plasma wave moves extremely fast, nearly at the speed of light, and is just a few microns long. Because it supports extremely high electric fields, it provides the ideal conditions to accelerate electrons and positrons to very high velocities. You may ask, why is this promising? Well, conventional accelerators are based on radio frequency cavities, which can only take electric fields that are at least 1,000 times smaller than those we get in plasma accelerators. This gives the theoretical possibility to, for example, reduce the size of SLAC at Stanford, the biggest linear accelerator in the world with 3.2 kilometers, to just over 3 meters. However, this plasma acceleration technology is not easy to master. Factors other than the magnitude of the acceleration field are also important, related to additional internal properties of the accelerated particle beams, that will determine the overall beam quality and the potential to use these beams for scientific and societal applications. When it comes to plasma accelerators, this beam quality still hasn't reached that of radio frequency cavities. So how can we tackle this? It's not easy. Current analytical models are valid under simplifying approximations, which make it difficult to predict all the features of the accelerated beams. So simulations are one of the only ways to get some predictions. In particular, particle-in-cell codes, or PIC codes, allow us to predict what is going to happen, as they require no approximations. As we know more and more about plasma laser interactions, the goal of the field is to produce actual accelerators. My goal with this thesis is to provide a new tool to optimize beam quality by making as few simulations as possible, in order to speed up progress. To do it, we'll use machine learning techniques, especially genetic algorithms, which belong to the second part of the title. Don't give up on me now. Let me try to clarify this for you. A genetic algorithm is based on Darwin's theory of evolution. We start with lots of individuals of a population. Some of them are a better fit for the environment than others. These better individuals prosper, making sure their genes propagate to the next generation. This can be done through mutation, a small random change on the genes, or a crossover, combining two or more fit individuals to create another. The remaining less fit individuals, well, they're not so lucky. This is the fundamental idea behind the genetic algorithm. In our case, the individuals will be a set of parameters of the laser plasma system, and the function that we want to maximize will represent the fitness of the individual. You can try to maximize the accelerating field, or just try to improve the beam quality in some other way. Some variables can be limited, as for instance the energy of the laser, to get more realistic final results. This is just a brief explanation, as more and more machine learning techniques can be added to this method, making it faster and more efficient. However, machine learning is still seen as something opaque, as sometimes the scientists struggle to interpret the results. We'll tackle that by still being able to see what's happening in all the iterations of the method and look at bigger improvements closely to understand what's really happening. The final goal of my work is to incorporate an exciting booming area as machine learning into advanced plasma physics computer programs, and thus contributing to the way we still have to pave towards these new accelerators. If you want to learn more about some topics that I didn't explore in detail, please follow the links in the description. So, I guess it's time for me to get back to work. Bye!